Welcome to week 4 of deep learning. So this week we'll talk about tricks of the trade. At the lectures, at the session, we will learn also about GPU programming, but that will be hands-on, so I will not talk about that. Tricks of the trade is really important for making deep learning work. So in this lecture I will talk about two aspects of tricks of the trade. First one is how do we ensure faster convergence and convergence at all. We do that by clever initialization and by different other tricks like gradient clipping and batch normalization. Then the second part is about getting better predictive performance, better generalization performance, and we do this by different types of regularization. Weight decay, weight priors is kind of the classical way. More recently we have also learned about or there's been developed a technique called dropout, which has actually showed really nice results, and I'll talk about all these techniques. And then in the end I will have a recap of this lecture today. Yes, first, how do we achieve faster training? So we can do that by, for example, clever initialization, and here is a famous Global initialization, which simply says that if we look at a specific weight, wij, then we should initialize it as a random normal variable. That's not so surprising. So we use the rand_n random number from your computer, but the important thing is the prefactor. And you can see here is a prefactor with a square root, and we have a factor of 4, and then we divide by the number of weights coming into the network plus the number of weights above. And why do we need this number? And here we have that we have a weight connecting a layer with layer I with layer j, and each of them has ni and nj weights. So the weight matrix wij has ni times nj components. So here's an outline of the derivation. It's actually not so complicated. Remember, when we train, we have a forward pass, and what we look at is kind of the statistics of the activations as we propagate forward, and we also look at the statistics when we do the backward pass in the back propagation. And these two statistics should kind of stay on being of the order of 1. We don't want to have vanishing signal we send forward or vanishing signal we send backwards. So in order to achieve that, we can do a little bit of analysis. Sorry, the wrong way. So we have that actually to retain the variance forward, and this is assuming that we have tangent hyperbolic activation functions. Then we need the square root of 2 divided by nj, the number of connections in the layer the post number of connections. And to retain the variance when we do back propagation, we need this 2 over ni, when ni is the preceding number of weights. So a compromise between these two is this global initialization. If you have ReLU units, then you actually have the fact that you actually truncate activation kind of for all the negative, and that means that you actually have to so this is actually what I'm saying. This is the activation for ReLU. So if you have tangent hyperbolic, instead of having a 4, you should have a 2. And this is because that ReLU kind of removes half of the variance, because it truncates all all negative signals. And this kind of balance between the two in the global initialization only kind of works if you have more or less the same number of connections going forward and going backward. Yes. So there are also many other ideas. There's like Sachse made a very nice paper, and collaborators made a very nice paper where they analyzed the dynamics of deep networks, deep linear networks, and they found that actually orthogonal initialization gives a much faster convergence. They also found that it's not a question of local minima, but of local saddle points, and in order to get out of these saddle points fast, you need to have this orthogonal initialization. And there's also a lot of other work recently, so this is really an open field, and I think personally there's a lot of room for improvement on using these methods. It should also be said that these methods work for feed-forward neural networks. They are not so well established for recurrent neural networks. It's a little bit harder there because you have this weight sharing between the different layers, and you also have that you might have that the signal is informative at some time step but not at another time step. So if you do some shared normalization, you risk removing the really informative signal. So recurrent neural networks are a little bit more complicated to use these methods on. Another method that we use a lot in practice to avoid ending up in not a number situations is what is called gradient clipping. And the idea is illustrated here. We have this energy landscape which is quite flat, and then at some point we kind of meet the wall, and if we take our small gradient descent steps, we might at some point end up a place where the gradient is very large, and then we make a very, very big jump to some completely different weights. And that could be that in that very large jump we might lose a lot of information about a good minima we were approaching. So in order to avoid having these very large steps, we can simply say that we truncate the gradients maybe at a value of 1 or something like that. It's quite easy to set that up in Lasagna, as you have also probably seen in the exercises. So this was a little bit about initialization and gradient clipping, two really important points to make your network converge fast.